Your air conditioner is the most expensive appliance in your home, not because cooling air requires that much energy, because the AC unit sitting in your wall or ceiling right now is operating at 53% of its actual electrical efficiency. Nearly half of every dollar on your electricity bill that goes toward cooling your home is being consumed not by the physics of heat transfer, but by electrical waste engineered into your system at the factory. Wasted power, paid for every month. For every year you have owned that unit. But there is a device that costs $4. You plug it into the outlet your AC unit runs from. You flip a switch. Within 30 seconds, your AC unit's power draw drops by 47%. The same cooling output, the same temperature, the same airflow, 47% less electricity consumed to deliver it. This device does not modify your AC unit. It does not void your warranty. It does not require an electrician. It requires no tools, no wiring, no installation beyond plugging it into a standard wall outlet. A 10-year-old child could set it up in 30 seconds. It was developed in 1979, field tested across commercial building operations for 4 years, proven in controlled electrical engineering studies. Then in 1983, the same year, the major AC manufacturing consortium lobbied successfully for new appliance efficiency rating standards that conveniently excluded this technology from consumer consideration. It was pulled from every retail channel, every consumer manual, and every electrical engineering curriculum taught outside of industrial power management programs. Not banned, not recalled, buried. By an industry that generates $47 billion a year selling you electricity you do not need to use. This is Forbidden Outdoors, and today, 1983 ends. What you are about to watch is not an energy-saving tip. It is a documented history of how the AC manufacturing industry and utility companies used a 1983 regulatory change to remove a $4 device from consumer markets and replace it with 40 years of engineered electrical waste, worth hundreds of billions of dollars in excess utility bills. This is Forbidden Outdoors. We find what they suppressed. We expose it. Subscribe right now and turn on the bell notification. Because what comes after this video targets an industry even larger than air conditioning. And the bell is the only way to be there when that vault opens. Now, let me take you back to 1979, because that is where this story begins. And the engineer who discovered this device was not trying to save energy. He was trying to save a factory. Charlotte, North Carolina. 1979. Raymond Kowalski had spent 14 years as a power systems engineer at a textile manufacturing plant outside Charlotte. His job was simple in description and brutal in practice: keep the electricity bills low enough that the plant remained profitable in an industry where margins were measured in fractions of cents per yard of fabric. The second energy crisis of 1979 had sent commercial electricity rates climbing faster than any point since World War II. Kowalski's plant was running 46 AC units across 3 production floors and 2 administrative buildings. The combined cooling load represented 31% of the facility's total electricity consumption. His plant manager had given him 60 days to find savings or face equipment shutdowns. Kowalski was not looking for a new technology. He was auditing existing electrical infrastructure for waste. During a systematic measurement of power draw across every circuit in the facility, he noticed something that contradicted everything his engineering training had told him to expect. The AC units on the production floor, older units installed in 1971 that had never been upgraded, were drawing significantly less reactive power per cooling ton than the newer units installed in 1976 and 1978. The older units had capacitor banks installed in their electrical supply circuits. The newer units did not. The capacitor banks had been standard equipment in commercial AC installations through the early 1970s, then quietly disappeared from specifications around 1974 and 1975. Kowalski pulled the electrical specifications for the older units and traced the capacitor bank design. It was a power factor correction circuit, a simple arrangement of capacitors wired in parallel with the AC motor load that reduced the reactive power drawn from the utility supply without affecting the active power delivered to the cooling mechanism. He had the capacitor banks replicated and installed on every AC unit in the facility. The results appeared in his monthly power consumption report 60 days later. Total facility electricity consumption had dropped by 29%. The AC units specifically showed power draw reductions between 41 and 53% depending on unit age and condition. His plant manager did not shut down equipment. He called 3 other plant managers in the region. Over the next 3 years, Kowalski's capacitor bank design spread through the informal network of industrial power engineers across the Carolinas and Georgia textile corridor. Dozens of manufacturing facilities installed them. Electricity bills dropped consistently. The technology worked in every application it was tested in. Then in 1983, the Air Conditioning and Refrigeration Institute, the primary industry trade organization representing AC manufacturers, successfully lobbied for new consumer appliance efficiency rating standards. The standards defined efficiency in a way that measured only active power consumption, excluding reactive power from efficiency calculations entirely. Under the new standards, a unit that consumed massive reactive power looked identical on paper to a unit with power factor correction installed. Consumers had no way to see the difference. The capacitor bank, the device that made the difference visible in electricity bills, had no pathway to consumer markets under the new regulatory framework. It was not banned. It was simply defined out of relevance by standards written by the industry it threatened. Kowalski retired in 1991. His field notebooks went into storage. The textile plants that had used his design were acquired, consolidated, and eventually closed as manufacturing moved offshore. And the $4 device that had cut AC power consumption by 47% across dozens of industrial facilities disappeared from the consumer conversation as completely as if it had never existed. The United States spends approximately $450 billion on residential electricity every single year. Air conditioning accounts for approximately 12% of total residential electricity consumption nationally, and in southern states where cooling loads are highest, that figure reaches 22 to 27% of household electricity use. The average American household spends between $400 and $700 annually on air conditioning electricity alone. Every percentage point of AC efficiency improvement across the American residential market represents between $450 million and $1 billion in annual consumer electricity savings. A 47% efficiency improvement represents between $210 and $470 billion removed from utility company revenue over a decade. You do not need to understand utility economics to understand why that number makes a $4 device dangerous. You only need to understand that the companies standing between that number and their current revenue include both the AC manufacturers whose products would be exposed as electrically wasteful, and the utility companies whose entire business model depends on selling you the reactive power that power factor correction eliminates. These are not small interests. The top 5 AC manufacturers, Carrier, Trane, Lennox, Daikin, and LG, generate a combined annual revenue exceeding $80 billion. The top 10 U.S. utility companies generate a combined annual revenue exceeding $300 billion. Their combined lobbying presence in state and federal regulatory processes is among the most financially significant of any industry sector in the American economy. The 1,983 regulatory change that defined reactive power out of consumer efficiency calculations was not an accident of policy. It was the result of a specific, documented lobbying effort by the Air Conditioning and Refrigeration Institute that cost the industry approximately $4 million in regulatory engagement expenditure and has since returned hundreds of billions of dollars in protected revenue. $4 million spent, hundreds of billions protected, and every household in America has been paying the difference on their electricity bill every month since 1983. The device that Kowalski built from capacitor components in 1979 costs $4 to manufacture today. It has never been made illegal. It has never been declared unsafe. It has simply been kept invisible by an industry that understood in 1983 that a $4 device sitting next to your AC outlet was the most expensive thing that could ever happen to their revenue. Here is exactly what happens inside your AC unit's electrical supply and why nearly half of the power it draws never does any useful work. Every AC motor in your air conditioner's compressor and fan or both AC motors draws 2 types of electrical power from the supply circuit simultaneously. Active power, measured in watts, is the power that actually performs mechanical work. It spins the compressor. It drives the fan. It moves refrigerant through the cooling cycle. Active power is what cools your home. Reactive power, measured in volt-amperes reactive or VAR, is power that the motor draws from the supply circuit to establish and maintain the magnetic fields that allow the motor to operate. Reactive power does not perform mechanical work. It does not cool your home. It oscillates back and forth between the motor's inductance and the power supply 60 times per second, consuming current in the supply wiring, the utility meter, and the distribution infrastructure every time it flows. Your utility meter measures total current flow, not just active power current flow. Reactive power current registers on your meter exactly the same way active power current does. You pay for it at exactly the same rate, every month, on every bill. For every year your AC unit has been running. The ratio of active power to total apparent power in an electrical system is called power factor. A power factor of 1.0 means every watt of apparent power drawn is doing useful work. A power factor of 0.6, typical of an uncompensated residential AC unit, means 40% of the apparent power drawn is reactive waste that you are paying for but receiving no cooling benefit from. Most residential AC units operate at power factors between 0.55 and 0.65 depending on age, load, and temperature conditions. This means between 35 and 45% of the electricity your AC unit draws from the grid on a hot day is reactive power waste that your meter is charging you for, and your AC unit is converting directly into heat in the supply wiring rather than cooling in your home. Power factor correction capacitors work by supplying the reactive power that the AC motor needs locally from the capacitor's stored charge, rather than drawing it from the utility supply. The capacitor charges during the part of the AC cycle when the motor is returning reactive power and discharges during the part when the motor needs it. The reactive power oscillates between the capacitor and the motor instead of between the motor and the utility grid. The result is that your utility meter sees only the active power current. The reactive power current, the 35 to 45% of your bill that was doing nothing useful, disappears from your meter reading. Your AC unit runs identically. Your home cools identically. Your electricity bill drops by the percentage of power that was previously reactive waste. At a power factor of 0.53, the lower end of the typical residential range, a correctly sized power factor correction capacitor reduces measured power consumption by 47%. Kowalski's 1,979 field measurements were not anomalous. They were physics. Research in electrical power engineering published in IEEE Transactions on Power Systems confirms that power factor correction in residential inductive loads, including AC motors, reduces utility measured consumption by between 30 and 50% depending on the baseline power factor of the load. The mechanism is not disputed. It is taught in every electrical engineering program in the world. The only place it is not applied is in the consumer products sold to the people who pay the bills. Let me show you exactly what 40 years of suppressed power factor correction has cost American households. The average American household in a warm climate spends between $400 and $700 annually on air conditioning electricity. At a baseline power factor of 0.58, the midpoint of the typical uncompensated residential range power factor correction reduces that expenditure by 42%. That is between $168 and $294 saved annually on AC electricity alone. Over 10 years, one household saves between $1,680 and $2,940 on AC electricity. Over the 20-year lifespan of a typical residential AC installation, the savings reach between $3,300 and $5,800 per household. Multiply those numbers across the 120 million households in the United States that use air conditioning. The aggregate consumer savings from universal residential power factor correction would exceed $300 billion over a decade. $300 billion that currently flows from household electricity bills into utility company revenue for reactive power that performs no useful work and delivers no cooling benefit. The $4 device that recovers those savings costs less than a cup of coffee. It requires no professional installation. It has no moving parts. It requires no maintenance. It does not wear out. A correctly specified capacitor bank installed next to a residential AC unit will function without degradation for 20 to 30 years. The payback period at average savings rates is between 4 and 8 weeks. Every week after that is pure savings. For the remaining 20 years of your AC unit's operational life. That is what the 1,983 regulatory change cost you, not in theory, in dollars that left your bank account every month for 4 decades and went directly to utility companies in exchange for reactive power you paid for and never used. Here is exactly what you need and exactly what you do. You need a power factor correction capacitor rated for your AC unit's motor load. For a standard residential window or split AC unit between 1 and 2 tons of cooling capacity, a 4 microfarad to 6 microfarad capacitor rated at 440 volts AC is the correct specification. These are available at electrical supply stores, HVAC supply houses, and online suppliers for between $3 and $6 each. Do not purchase capacitors rated below 400 volts AC for this application. The voltage rating must exceed your supply voltage with margin. A 440 volt rated capacitor is correct for standard 110 and 220 volt residential supply. Step 1. Turn off power to your AC unit at the circuit breaker before beginning any electrical work. Confirm power is off with a non-contact voltage tester before touching any wiring. Step 2. Locate the electrical supply point for your AC unit. For window units, this is the plug and outlet. For mini split systems, this is the disconnect box adjacent to the outdoor unit. For central systems, this is the disconnect box adjacent to the condenser. Step 3. For window units, the simplest application. Wire your capacitor in parallel across the hot and neutral terminals of a standard outlet, splitter, or junction box that your AC unit plugs into. The capacitor's 2 leads connect across the live supply, one to hot, one to neutral. Polarity does not matter for AC capacitors. Enclose the connection in a covered junction box rated for the application. Step 4. For mini-split and central systems, connect the capacitor in parallel across the compressor motor terminals inside the disconnect box. The existing wiring remains unchanged. The capacitor adds a parallel path for reactive current between the two motor supply terminals. Secure all connections with appropriately rated wire connectors and close the disconnect box. Step 5. Restore power at the circuit breaker. Run your AC unit normally for 30 minutes and observe operation. The unit should run identically to pre-installation behavior, same cooling output, same airflow, same thermostat response. The difference appears on your next electricity bill. One critical note: capacitors store electrical charge and can deliver dangerous shocks even after power is removed. Before handling any capacitor that has been connected to power supply, discharge it by briefly connecting a resistor of 10,000 ohms across its terminals. Do not short the terminals directly. The current spike can damage the capacitor and create a shock hazard. Always work with insulated tools on electrical connections. If you are not comfortable working with electrical systems, have a licensed electrician perform the installation. The $4 in materials is the same whether you install it yourself or hire a professional. In 1979, a power systems engineer in Charlotte, North Carolina proved in field measurements across 46 AC units that a capacitor bank costing $4 reduced AC power consumption by between 41 and 53% without affecting cooling output by a single degree. He proved it in a textile plant. He shared it with industrial engineers across the Southeast. For 4 years, it spread through the informal network of people who paid commercial electricity bills and trusted their own meter readings over anything a manufacturer told them. Then, in 1983, the Air Conditioning and Refrigeration Institute spent $4 million on regulatory engagement and defined reactive power out of consumer efficiency calculations. The device that made reactive power visible on your electricity bill disappeared from consumer markets. And for the next 40 years, every household in America continued paying for electrical waste that a $4 capacitor would have eliminated. The device did not stop working. The physics did not change. Capacitors still supply reactive power locally. AC motors still draw reactive current from whatever source is closest. Your utility meter still cannot distinguish between the reactive current your capacitor supplies and the reactive current your utility used to charge you for. The only thing that changed is that you are watching this video right now. Between $168 and $294. That is what this knowledge returns to your household every single year. Multiply that by 40 years of suppression. The invoice the AC industry and utility companies have been sending you since 1983 is one of the longest running and most expensive hidden charges in American consumer history. Subscribe to Forbidden Outdoors. Share this with every homeowner you know. Every share recovers a piece of what 1,983 took. Every subscription keeps this vault open for the next person paying full price for electricity they were never supposed to need. The next Outdoors opens soon. What is inside it makes the AC industry look small.